Today we're going to try to answer the question, what do you do with a differential equation if you can't find the solution? Well, there's still some things you can say about it. You can do a qualitative analysis. That means describing what it's like, its qualities. And we're only going to do that for first order equations. This process for higher order equations and for systems of equations is much more complicated, and you get that in second semester differential equations. Alright, so qualitative analysis of model solutions of a first order equation, dy dt equals f of y. What do we do? Well, there's two things, and these are the main 2 points for today. If it's difficult to solve, you can, if it's an autonomous equation, remember autonomous equation means dy dt equals f of y, the dependent variable alone. No t over on the right hand side. You put it in a normal form, first derivative on the left by itself, equals f of t and y. If t isn't there, then it's autonomous. In this case, you can do what's called a phase line diagram. And for higher order equations, a phase plane or a phase space in general is harder to draw. For first order equations, we have a phase line, a one-dimensional qualitative analysis. Will help us to actually sketch solutions in the plane, right? Solutions of these curves y equals f of t that satisfy the differential equations. And then, even if it's not an autonomous equation, we can still try drawing a slope diagram or a direction field. It's often called slope field, I think your text calls it, which also uses dx dt equals f of x. Same thing, just with x the dependent variable. Alright, now I just want to point this out. Books don't seem to point this out for some reason, but when you have a first order single autonomous equation, you can actually always write at least implicit solutions, because you can turn this upside down and write dt dy equals 1 over f of y, separate variables and get t by integrating dt on the left equals integral dy over f of y. So you take the reciprocal, dt dy equals 1 over f of y, separate variables and integrate, and you get this, and you can write t at least in an integral form and get implicit solutions in integral form for t as a function of y. And so sometimes you can go to the computer and get nice plots of these using that reverse thing. We aren't going to do that here. I just mentioned that in case you got an industry and have to plot the solutions. That's a way you can do it. But instead we'll use direction fields, slope fields, for equations that are autonomous or non-autonomous. And for equations that are autonomous, we can use the phase line to get a little better understanding of what's going on. So here's the direction field analysis for general equations, dy dt equals f of t and y. What we can do is we can assign one line segment or a directed line segment vector to each point ty in a region of the ty plane when we're solving dy dt equals f of ty. That should remind you of calculus, where you had vector field, right? It was a vector field. You assigned a vector to each point in the plane. It might be the electric strength vector. It has a direction and a length for the strength. Or a gravitational field. Each point has gravity acting in a certain direction with a certain strength. So you put a vector there. Similarly, a slope field or direction field, we put a little line segment at each point in the ty plane, and it tells you the slope at which solutions pass through that point. And you can use vectors if you want. Sometimes people like to use vectors, but the length is not so important. It's just you show the slope of it. So that will be a direction field. At each point, you plot the slope. Well, how do you know the slope at each point in the ty plane? Well, it's obvious. It comes right out of the differential equation. At each point ty, the slope is f of ty, right? Just plug ty in and see what the slope is. So it's actually very easy to plot these, and computers are very good. There's nice software packages for MATLAB and everything else where you can quickly plot these things up. And look, you can get a nice qualitative picture of how the things go through by looking at the flow field, kind of like if you were looking down on a lake and you see the ripples going around. You say, oh, the water's flowing like that. Similarly, we draw little line segments here and we say, oh, the solutions are flowing like that, tangent to the little ripples, the little line segments. So that's the idea of a direction field. You draw the little line segments that are the slopes in the ty plane. You see kind of how something would flow through that direction field. that's a solution, right? The solution has to be tangent at every point. That's what the differential equation says. The slope of the tangent line of the solution is equal to the slope of the line segment that you drew. F of ty is the slope. So here's an example. dy dt equals y minus t squared. I can actually solve this one. It's a linear equation. We can use our linear equation method and write the solution up in terms of an integral. But even without doing that, I can get a good idea what the solutions are supposed to look like, which might not be a bad idea since it's easy to make a mistake. You should see if your solutions look like this, right? The direction field can be sketched one segment at a time. I can plug in t equals 0, y equals 0. Oh, the slope is 0 at the origin. T equals 1, y equals 0. Oh, the slope is 0 minus 1 at the point 1, 0. And so I try and, oh boy, that's tedious. It really helps to do these things when you have to draw these by hand, to draw what's called isoclines. You can find curves along which all the little direction field segments have the same slope. And then once you have one of those curves, you just draw a slope, 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 slope all along that thing. And here's an example here. This is the direction field for the one we're doing. We'd have to plot all these little line segments, see the little red line segments, and each plug in a t and y, find the slope and plot it at that slope. Find the t and y, plug in t and y and find the slope and plot it. Boy, that takes a long time. But if I can just get these curves here, which are the isoclines, along each of these curves, this one might have slope, looks like about 2/3 or something. Every line segment has the same slope. Now the blue ones are the solutions. The blues have to follow the slope, right? At each point they touch, they're tangent to the little red line I drew. So these are the solutions, but I get the solutions by hand. By first writing these isoclines, when I know all the little line segments here will have the same slope. Then I draw all the line segments of that slope, and for each of these, and pretty soon I have a lot of these little line segments showing you how water or whatever it is would flow through here. And here's the solution curves to this differential equation. They follow the flow of the little line segments. All right, so that's what we're trying to get at. And so first I'm going to come up with some isoclines. You don't have to draw these, but you'll have trouble finishing the test on time if you just try to draw 100 little line segments instead of 10 isoclines and 10 segments on each. It's a lot easier. So here's the differential equation. Here's dy dt equals f of ty. An isocline means constant slope. That means f is equal to a constant. So I put y minus t squared equals 0. And every little line segment I draw will have slope 0. If I put y minus t squared equals 1/4, every line segment through that curve will have slope 1/4. Y minus t squared equals minus 1/4, every line segment through there will have slope minus 1/4. So let's try this. I put y minus t squared equals 0, and I get y equals t squared, the basic baby parabola you learned in algebra, right? Along the parabola, y equals t squared, every line segment in the direction field will have slope 0, right? dy dt equals 0. So here's the parabola right here. And look, oops, wait a minute. I can't do it. Let's be, here's 0, 0, sorry. 0, 0. This is the parabola y equals t squared, and on every line segment I draw on that parabola is horizontal, slope 0. Now I go up here and I put y minus t squared equals 1/4. That's easy to draw too. Y equals t squared plus 1/4 is the same parabola, shifted up 1/4 unit, right? Because I added 1/4 to every y coordinate. So let's see, 1/4 is about right here. At 0, 1/4. And then maybe it's this one probably. I draw line segments of slope 1/4. And then I go up and say y minus t squared equals minus 1/4. Well, that's the y equals t squared curve shifted down 1/4. So it goes from 0 minus 1/4 by here. So every line segment along this parabola, y equals t squared minus 1/4, has slope minus 1/4. And I do that for a whole bunch of these, and I fill up enough spots that I can kind of see how to draw blue curves here. You know, you kind of have to eyeball it and just guess, but still you can see what the solutions behave like, right? They go down here for a while, and then they come up a little bit. They get pretty horizontal, and then they go back down. Up here, they're going to go down and back up. You can see that kind of quality of solutions, right? This one's going to have an inflection here. And so you derive that just by drawing the direction field, and you can do that for any differential equation for which you can calculate the right-hand side, right? So that's the direction field. You can do that for dy dt equals f of ty, a quite general differential equation of first order, right? In normal form. Now, what about the special case of autonomous equations? Dy dt equals f of y alone, no t in there. Now we can additionally do a phase line analysis. And we'll say first, if C is a critical point, that's a point where f of y equals 0. If a value y equals c that makes f of y equals 0 is called a critical point. And then there's a corresponding, we said before we did the separation of variables, there's a corresponding stationary or constant solution, y equals that number c, right? Because if c makes f of y equals 0, y equals c has derivative 0 also, and it satisfies that y equals c satisfies the differential equation. It is a solution. So you want to plot all those. And what we're going to do is plot them on the y number line. We're not going to plot the plane yet. The phase line is actually the y line, the dependent variable line. And so we'll plot a point C on the line where there's a stationary solution. Then, on intervals where f is continuous and not 0, otherwise you have a stationary point, you can get implicit stationary solutions, like I said, by writing t equals the integral dy over f of y by separating variables and integrating. That might give you a few ideas how to plot some trajectories in there. But bear in mind when you draw these phase diagrams that any autonomous equation, if you replace t by t minus c, well, since this doesn't depend on t, you get the same, you get another solution. So if y equals y of t is a solution, y equals t minus c, the whole curve shifted rigidly like a stiff wire slid over is again a solution. You can translate in t, think of it as time translation or something, and again get a solution. If y equals y of t is a solution, y equals y of t minus c is also a solution. So we bear these in mind when we're going to draw our solutions using a phase line. And then I'll just point out here the properties before we actually draw the phase line. Here is a solution, y equals e to the 2 times quantity t plus 1 of y prime equals 2y. This is the same curve. Actually, I should do the light green one. This is y equals e to the 2t is a solution of this differential equation. Y equals 2 times, replace t with t minus 1, that's the red curve, is also a solution. Just take this one and slide it over. Y equals 2 times t plus 1, take this one and slide it over, it lands right on this one. And so on. Each of these curves, this one is slid over 2 units. Replace t by t minus 2. It translates at 2 units in the t direction. This would be 2 plus 2. Whatever is subtracted is a shift, so there's a typo there. Yeah. All right. Or maybe it's just not visible. All right, but that's the idea. Is they translate over one solution to the next when you're drawing your autonomous solutions. Here's an interesting problem model where you have a basic population model, dy dt equals a constant times y. Remember that one? dy dt equals ky or ry, your population model from calculus. Well, what if you also have a rate of birth proportional to the population present and a death with death rate proportional to the population present. So you have these rates R1 and R2, the birth rate and the death rate that go in there are constants. And maybe there's also immigration. In members of the species are leaving per unit time. And then at time 0 you have initial population y0. This would be a differential equation where R1, R2 and N are constants. Well, how can you solve this? If you define R equals R1 minus R2, this constant is the difference, you turn into this, which is the basic population model plus another non-homogeneous term, you could solve this as a linear equation or as a separable equation, it doesn't matter. And it's pretty easy, but we can also use this to illustrate how to get a pretty good sketch of the solutions without even solving the equation. For instance, consider the case, suppose the growth rate, which is the birth rate minus the death rate, is 0.8, and 100 members of the species leave per unit time. And you have this differential equation, dy dt equals 0.8y minus 100. Y is or equals start with 100 creatures. So the isoclines are the right side equal a constant, 0.8y minus 100 equals m, some constant. I like m because it's slope, right? This is the slope of the little line segment you're going to draw. And so here it is. It shows the isoclines for this one are easy. Right, you put m equals minus 20 and you get 0.8y minus 100 equals minus 20. Well, that's a line, right? Y equals 100. And if you put m equals 0 in here, then you got 0.8y minus 100 equals 0. Now you've got the horizontal line y equals 125. Put m equals, put the right side here equals 20, then you get the isocline y equals 150 and so forth. So you draw line segments of slope 20 along the horizontal line y equals 150. Line, horizontal slope 0 line segments along the null line, we sometimes call it when it's slope 0, y equals 125 and so forth. So here at 125 we draw slope 0, and actually this is also a solution by our first comment we have up there, right? Whatever constant makes the right side 0 in an autonomous equation, since it's automatically separable, is a constant or stationary solution. And then along this line, y equals 100, we have the, let's see, we didn't do that one, did we? We did slope 20 along y equals 150. So here's 150, and these are slope 20 segments here, all along there. They don't look like because the axes aren't scaled the same, right? 1, 2, 100, 200. But these are slope 20 segments. And so now you try and draw, if this is your initial condition right here, at time 0 you have 130 creatures. This is your unique solution to the initial value problem. If we start with 125 creatures, we're just going to keep 125 creatures. Now you can see qualitatively what happens from this diagram. If you start with 125 creatures, it'll stay the same. If you start with less, your population is going to die out. You can predict the time based on how many you start with. With 100 creatures, you're going to last about 2, whatever it is, years. But if you start with more than 125, it's going to grow exponentially forever. Well, there's something wrong with the model. It's going to be pinky in the brain, right? You overgrow the earth. And the model is not accurate for all time and eternity, but for initial estimates, while there's plenty of food and not disease and war and stuff, this might be a reasonable model, and you can see exactly what happens qualitatively just by drawing the direction field there for this autonomous solution. And you also have this property, each one of these things, this one slid over this way gives this one. This one slid over this way gives this one. They're all just the same curves slid over. This one slide over here lands on this one, slide this one over here lands on this one. This one lands on itself. All right. So there's drawing a direction field for an autonomous equation, but once more, sometimes these direction fields are still a little tricky. This is where we bring in the phase line that we started to talk about. We can do it with 2 graphs. So the critical points, or stationary points, or equilibrium points, it's called all 3, are the numbers c that make f of c equals 0 in the differential equation. Where'd it go? I guess it's up there a ways. dy dt equals f of y only. Whatever y value, c, makes it f of c equals 0 is a stationary solution. Plot a horizontal line in the solution space. Then, that's a critical point on the phase line, the y line. Between all the critical points, you then draw arrows to show which way solutions are traveling along in y. Is y increasing or is y decreasing? You draw arrows in those directions. And if the arrows go towards a critical point, a stationary solution, then you say it's an asymptotically stable point. But if they move away on both sides, then it's unstable. If it moves towards the critical point on one side and away on the other, then you say it's semi-stable. And there are more qualifications and more dimensions because like if you had a phased plane instead of a phased line, you could spiral around the points and then you have other kinds of solutions. So you do this in steps. You first draw the phase line showing the critical points and arrows on the phase line which way the solutions are moving. Then you turn the phase line up against the solution ty plane, and that helps you to actually be able to draw which way the solutions are moving according to which way the arrows are on the phase line. And then you can use the direction field in addition if you want. Here's a very important model in population dynamics. dy dt equals ry is the basic model. We saw that population grew for all time and eternity. That's not realistic. We modified it. We replaced the constant growth rate r with a linear growth rate. Right? R multiplied y here, take the y out. R times 1 minus y over k now multiplies y. So the growth rate is a linear function of y, r minus ry over k. Right? A constant plus a constant times y. A linear growth rate in y. So that what happens now is if y gets to be greater than k, then you'll get negative slopes here, and if y is less than k, but greater than 0 for population, then you'll get positive slopes. So the population will tend to increase to a stable level at k, which is actually, if you look at this, a critical point, right? If you put y equals k, then the right side is 0, so y equals k is a stationary solution, a constant solution. So we've noticed that. We first factor the right-hand side, right? It's dy dt equals f of y alone. We look at this. What are the values of y that make it equal to 0? Those are the critical points. Y equals 0 is 1, start with 0 population. Y equals k is another from this factor. There's only 2 critical points, stationary solutions. Then we can use the phase line to perform a qualitative analysis as follows. A lot of books like to draw this picture first. In the y versus f of y, this is f of y on this axis, not marked, I guess. Y versus z equals f of y or something. You draw the right-hand side function. In this case, we had the function ry times 1 minus y over k. Actually, I think this one is for a specific case. This is for the specific case when r and k are 1. Y prime equals y times 1 minus y. So what you do is you draw the right side, y minus y squared is a downward parabola. Then you can use that to see where is that equal to 0. Oh, it's at 0 and 1. Those will be the critical points in your phase line. So the phase line is the y number line. Each point that makes the right side equal to 0 is a critical point, 0 and 1. Then between each critical point you say is y prime positive or negative. Well, if y is between 0 and 1, then this is positive, and this is negative. Positive times negative is negative. So y prime is negative, you know solutions are going to decrease, right? Y between 0 and 1, this is positive, this is negative, the product is negative. So y prime is negative. The solutions, when you're between 0 and 1, no, it's positive. I'm sorry, I'm getting it backwards. Sorry. Positive, when this is between 0 and 1, times positive when it's between 0 and 1, is positive. So the y prime is positive. That means the solutions are increasing. They have positive slope. So you draw an arrow this direction, means solutions move towards increasing y values. Then you say, well, if y is greater than 1, then this is positive and this is negative. And so y prime is negative, solutions move in this direction, towards less positive y values. And similarly, when y is less than 0, you get negative times positive, and so solutions move in this direction. So this is the phase line. It just shows the direction that solutions move relative to the critical points. Now you take that phase line, y, and you turn it up like this. Oops. There it is. And you move move down towards y equals 1, up towards y equals 1, or down from y equals 0. And what you now realize is that the phase line tells you the direction the solutions are moving as a function of time, right? If I start with this initial population, at time 0 I have population, whatever, 0.1, maybe this is millions of creatures or something. Then what's going to happen is, what? Well, any point between here and here is increasing. So it increases, 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 increases. But it never gets to here because remember by the existence uniqueness theorem, nice functions like this that are continuous, where f of y is continuous and df dy are continuous, cannot intersect. If they did, it would violate uniqueness. So it comes up and it comes closer and closer, but it doesn't intersect this. And so you know that with any solution that starts between 0 and 1, stays between the stationary lines 0 and 1, it just moves up and approaches it asymptotically. All the other solutions, once you have one, is just that same one translated over, translated over. Same thing up here, solutions that have to move down but never reach the stationary solution, so they come down like that. You don't know exactly their shape, but you know how you can get it approximately? Here's the direction field. If I draw the direction field, here is a isocline, and for whatever the slope this is, and I just draw all my solutions tangent to it. Then I know about how quick they turn. So between the direction field and the phase line analysis, I know to draw two horizontal lines here. The solutions go up, up, up here. They have to follow this slope field, and same thing here, and same thing here. They have to keep going down from this point. They asymptotically approach it in the backwards time direction. All right, so there's how you can draw a nice qualitative analysis of solutions to this problem without actually ever solving it. Now you get the idea that hard problems that you couldn't separate variables or solve as a linear equation or use a substitution, any of those methods we did, you can still qualitatively look at solutions. This one's kind of hard actually. You can separate variables. Here's the logistic equation that we just wrote. Y prime equals y times 1 minus y. The logistic equation with r and k equal to 1. Oh, I guess I just put r equal 1. Oh, there it is. This is the general logistic equation. I'm sorry. And I separated variables for it, and you integrate both sides. And actually, you find that by separation of variables, you get this solution. You can look through it in notes if you want. It's not critical. But this is the integrated solutions for the logistic equations all look like this. It actually can be solved, even though it's not as easy as the previous problems we were doing. And you can sketch them, and then you can see that they really do look like what we already drew. All right, and so here's the general logistic model. I did the phase line 0 to 1 when k equals 1 and r equals 1, but now if I take a general r and k, it still has that same kind of picture, just 0 and k instead of 0 and 1. Well, you can actually get semi-stable critical points. I forgot to mention that on this diagram, these critical points are very important, right? This 0 is an unstable critical point. If you start with any positive population whatsoever, the model predicts the population will build up to k, which isn't true in reality. If you had one, they couldn't reproduce, right? But the model has this drawback. But the idea is if you have a very small population, it will increase to here. It needs to be tweaked for small populations not being able to defend themselves and so forth. But this is what the logistic model predicts. You can look at the phase diagram and see that these critical points are very important. All right. Now, similarly here, suppose I have a harder one. dy dt equals y times 2 minus y. This one I'm going to have a hard time solving. So what I do, it actually is solvable, but it's not, at least for implicit solutions. Finding explicit solutions is pretty difficult. But I can separate variables and get t as a function of y. Without doing all that tremendous work, because there's a bunch of integrations of partial fractions and everything else, I can notice, wait a minute, this right-hand side is a quartic polynomial. That means a 4th degree polynomial, right? It's quadratic, cubic, quartic, clinic, and so forth. 4th degree is quartic. And if I put z equals the right-hand side and plot y versus f of y, or z, here's what it looks like. we know how to sketch polynomials, right? Whenever you have this thing factored, the point, the intersection with the independent axis here, y in this case, is where a factor is equal to 0. So it's at y equals 0, y equals 2, and y equals 3. That's the only place you can touch the y-axis. Those are the critical points, right? On the phase line. So they're on the phase line below the y versus f of y plane. I'm doing more than is in the book, by the way. This is a real nice thing. Boyce and DePrima has a very nice book where they go through this in excruciating detail if you want to see even more. It's a classic text on differential equations if you want to check it out from the library or something. You can probably find a copy online too. But that'll give you the critical points immediately because the polynomial is already factored, right? Now I just have to draw my arrowheads between these points according to whether it's positive or negative. One thing you know about this is when you have a 0, y equals 2 in this case, or a factor, 2 minus y, of even multiplicity, the polynomial is going to be tangent and bounce off. But if you have a factor of odd multiplicity, it's going to pass through. And actually, if you have multiplicity greater than 1, it's going to be tangent and pass through in the odd case. Multiplicity 1, it just passes through at a given slope. Multiplicity 2, it bounces, or even multiplicity, its tangent bounces off. Multiplicity odd greater than 1, it comes down as tangent and passes through afterwards. So you know how to draw these pretty well, and you learn in calculus how to do all these concave up and concave down, increasing and decreasing. We don't need to go into all that detail. We find the critical points and figure out by plotting a few points if you want. Fourth degree polynomial has at most 3 points where it changes direction, and one of them is right here because we know it turns right here. That leaves 2 other, in order to make it go through this point and this point, it must look like this, right? We know immediately it can have at most, 4th degree polynomial, at most 3 of these points where it has a peak of a mountain or a bottom of a valley, right? And we know there's one right here, so in order to turn down here, it has to have one here. In order to turn down here, it has to have one here. So we know it looks like that without being real detailed. This is a computer sketch. You don't have to make this accurate. Make it the right shape and figure out, oh, well, where f of y is positive, that means y dt is positive. The arrows go this way. Positive over here between 2 and 3. The arrows go this way. But greater than 3, the right-hand side is going to be negative, so the solutions are going to move this way. Similarly over here, for y less than 0, we see that this right side is negative because this is its graph. And so the y dt will be negative, solutions will decrease, right? This is the y number line. Now, having done the phase line, I can immediately get a phase diagram. What I do is I draw at each critical point, 0, 2, and 3, a horizontal line as the stationary solution, and then between each pair of stationary solutions and above and below the last ones, I sketch these curves with the appropriate slopes. Direction field really helps. See, these are really steep this time, so I need to know to draw these really steep. But they asymptotically have to approach this line because they can't intersect. And in between here, they go like this. I draw a slope field to fill it in. But like the direction, the phase diagram tells me that between these two, they just go up, 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 up. Right? From this one here, it goes only down. Between these two, it goes only up. Up here, it goes only down. So you know which way to draw the curves. You know that they horizontally translate. You can get a pretty good sketch of this just by drawing a few direction field segments and the stationary solutions and horizontally translating these. Isn't that great? So there's our qualitative analysis of solutions. Here's a model for spread of disease. Maybe you can try this on the COVID virus or something. This is actually not the best model. There's much better models than this. But this one actually, if you write it out, turns out to be here the rate of infection is proportional to the number of infected times the number of uninfected. N is the population. So N population minus the infected. And so if you have twice as many infected, that doubles the infection rate. If you have twice as many susceptible, then it doubles the infection rate. If you have twice as many of both, it's 4 times the infection rate, right? So you solve it and you actually find out that's the logistic model. That's just for fun. You don't have to do that. And there's other ones. Here's another model, population model, where you replace the growth rate with a quadratic. Y times y minus 2. And you can draw its phase line. here's the graph of f of y versus y. It touches at 2 places, so those are the critical points where the plot of f of y versus y is positive, you draw a right arrow. Where it's negative, you draw a left arrow, and here's a positive, so you draw a right arrow. And once you have that, once again, you can draw the stationary solution, and you can draw, you can, just with the lightest sketch of the direction field, which you don't need necessarily, you can kind of get the idea. These come up like this, and these come down like this, according to the direction, according to the phase line, right? Which also, if you drew these for negative populations, you have them come up like this. This illustrates an interesting thing, since you're coming towards this critical point and on one side away on the other, 0 is a semi-stable critical point. There's also a solution here, I didn't sketch it. And this stationary point where it's the arrows are approaching on both sides is asymptotically stable since you both approach. People always ask, is there stable but not asymptotically stable? Not for these, but in more dimensions, yes. So we may see that later in the course. All right, so here's the problems. Take a look at these and ask me some questions.